Hariom. In this video, we discuss the physical significance of self-inductance. We have seen that if you are trying to send a current through an inductor, the inductor will be opposing it. If you are trying to increase the current, it goes against it. If you are trying to decrease the current, again inductor will be acting against it. So the self-inductance is acting always against the cause which is producing it. So it is similar to what you call inertia in mechanics. Inertia is a tendency to oppose the change which is produced on a mechanical system. Or else it is the tendency of the mechanical body to continue in its state. In both ways you can take. So this is just like the inertia in mechanics, the inductance in the electrical circuit. So you can compare the equation that half L I0 square that we have found energy stored in the inductor can be compared with half mv square. This is similar. Therefore, we can say the role of inductance in electrical circuit is similar to the mass in mechanics. We know that the mass is measured as mechanical inertia for the system. So, self-inductance is measured as electrical inertia of the circuit. So, there is a physical significance like this you can identify. Okay. And one more point to introduce here is that we found the work done W is equal to half L I0 square in setting up the current maximum. Now, if I0 equal to 1 ampere, then you can find that L equal to 2 times the work done. So the electrical inertia can also be defined as the twice the work done in setting up a current of 1 ampere through the inductor. So self-inductance is relating with work done in the process. Okay. Then one more point is that it is easy to calculate the back EMF when the current is trying to increase or the circuit is made. But it is difficult to find the back EMF produced when the circuit is broken. Okay. So, how to identify that or how to solve that problem, or how to get the work done, the energy or the breaking of the circuit, what is the maximum energy developed during breaking, that we can identify from a practical circuit that you might have seen that when you switch it on for the fan and all, it starts working. When you try to switch it off, you can see a glow inside the switch. There is a spark possible. To avoid that sparking during that breaking of the circuit, we use a capacitor across it. That means the inductor and the capacitor will come in this particular form for that avoiding that spark between the switch. So when the switch is somewhere here, then breaking comes that the current that is developed in the inductor is not flowing directly through the switch. It starts flowing through the capacitor and it starts charging the capacitor. It charges the capacitor and therefore the current through the switch will be minimized and therefore the spark will be will not be seen. So in this case, whatever the energy that is stored in this inductor during that making, the maximum current is flowing, as to break that circuit, the whole energy is coming across the capacitor, that you can find it as half L I0 square will be equal to half CB square. Means the whole energy here, energy stored in the inductor U, that's equal to half L I0 square, is fully used up in charging the capacitor. Okay, so once the capacitor is charged to its maximum, across there will be a potential difference V, then half L I0 square is equal to half CV square, and this V you can take it as the EMF developed when the circuit is broken. This is a practical situation where you can use this conservation of energy. From this equation you can calculate the potential difference or back EMF developed during the breaking of the circuit. So these are certain extra points to be remembered in the case of self-inductance that we studied.